So the first phase diagram we'll look at is liquid vapor phase diagrams. And let's start with an ideal case. So remember, for an ideal case, for an ideal solution, we've got two components, A and B. So we'll have increasing mole fraction of B to the right here. And we'll have the pure B over here with some pure vapor pressure, and pure A over here with some pure vapor pressure. And then if they're ideal solutions, then the two components have vapor pressures in the solution that are given by Raoult's law. So we get straight lines here. So we've got P total, and we've got P for component B and the vapor pressure of component A. And so A and B add up to the total pressure. Great. So what this means is that if we were to look at a phase diagram, we can imagine two different phase diagrams. One would be one where we have pressure and we've got components, the composition on this axis. And in this case, we can see that if we have a pressure here equal to P star B, up here we're going to have, if we're at a really high pressure, we're going to have liquid. And if we're at a very low pressure, we'll have vapor. And so basically, if we lower the pressure, we'll have liquid B, we'll have liquid B. If we get low enough, B will boil right about here. So it's vapor. We could say the same thing about A. And the line between them, or as short as a straight line, is where we first see vapor appearing. And so we have here is a two-phase region where we have liquid plus vapor. And so we have a line where vapor first appears, and we have a line where the last bit of liquid disappears. So if we take a system with overall composition here and put that system at this pressure here, it's going to split into two phases. A vapor-rich phase with that composition, and a liquid-rich phase, or a vapor phase with this composition, and a liquid phase with this composition. And notice those compositions are not the same, right? Those compositions are given here and here. And so if we look, the vapor is going to be enriched in component B. And the liquid it's in equilibrium with is enriched in component A. And that makes sense, right? Because component B, remember, is the one with the higher vapor pressure. It's the more volatile stuff. So this just says that if you vaporize a mixture so that you basically vaporized about half of it, the vapor is going to have more of the volatile stuff and the residue is going to have more of the less volatile stuff. So that's pretty intuitive. We could write this on a different axis. So this diagram over here, we had pressure diagrammed, but we're working at constant temperature. So let's go ahead and annotate this, that this one was constant T, this diagram here, and we'll draw some dividers in here. We could just as well keep the pressure constant and change the temperature. And this is actually the more common thing to do with phase diagrams. What you have to remember is if something is very volatile, if it has a high vapor pressure, it has a low boiling temperature. And conversely, if it's not very volatile, if it has a low vapor pressure, it's going to have a high boiling temperature. So this is TB for component A. And this is TB, the boiling temperature, for component B. And what we find is at low temperatures, we just have liquid. At high temperatures, we have vapor. At intermediate temperatures, we have two-phase coexistence. So if I take basically a 50-50 mixture of those two things, A and B, and heat it up to about here, it's going to split into two phases. So we're going to have liquid phase over here, or sorry, vapor phase over here with that composition, and liquid phase with this composition. And so we can see basically that the residue, the liquid, is going to have a composition that's enriched in the thing with a high boiling point. And the vapor is going to be enriched in component B, which is the stuff with the low boiling point. So basically these two different diagrams, composition temperature versus composition pressure, are two different ways of looking at the same thing. Okay? So we have vapor at high temperature, or equivalently we could say we have vapor at low pressure. Okay, so let's look a little bit more at the temperature diagram since those are the more common ones. So let's just draw it a little bit bigger. And let's go ahead, sort of exaggerate this a little bit so we can see what we're doing here. Okay, so we've got XB, liquid, vapor, and we've got temperature on this axis. We can pretty much use vapor and gas interchangeably. What some people do is they say gas for something if it's a gas at room temperature, and vapor for stuff that you have to heat up to boil. It's not really much different. Anyway, what we see here is if I take a mixture of this composition and heat it up to about here, I get this vapor in equilibrium with this liquid. If I heat it up to here, I still get vapor in equilibrium with liquid, but two things have changed. The composition of the liquid and the vapor are not the same at the two different temperatures. So as I keep raising the temperature, I change the composition. But there's something else that's changing. What's changing is the relative amounts of these phases. As you can guess, if I keep going up, eventually I'll just get vapor. So it must be that as I go up in temperature, the amount of vapor is increasing and the amount of liquid is decreasing. And that can be shown by something called the lever rule, which is basically we look at these line segments here. Now I'll use different, here I use a dashed line here and a solid line. Notice something about the relative lengths of those two line segments as we go up in temperature. If we look here, let's count how many squares this is. This is roughly 1 square, 2 squares, 3 squares. Let's say this is 3.5 squares long. And this one over here is about 1.5. Okay, and so what that means is that in this scenario right here, actually I'll draw the arrow over there, if we prepare a system with that temperature and this overall composition, in other words, that's the total number, the mole fraction of B in the entire sample, regardless of which phase it's in, then we can see that there's going to be more of the liquid. This line segment shorter, we're closer to the liquid side. And so we can say the amount of moles of liquid is going to be 3.5 to 1.5. In other words, a greater number than 1, the moles of vapor. Okay? So basically, you should be able to say, okay, I have more liquid than vapor at this point, and the ratio of them is a ratio of 3.5 to 1.5. And over here, I can do the same thing. I can say the liquid is going to be, well, here I've got, let's see, 1 square, 2 squares, 3 squares, 4 squares. And over here it looks like 1. I'll just say it's 2. So now the situation's reversed. This segment's shorter. We're closer to the vapor side. So we've got 2 to 4 times the number of moles of vapor. So in other words, we have half as much liquid as we have vapor up here. So we went from having, this is about just over twice as much liquid, to now having half as much liquid as vapor. And so as we keep going up, the amount of liquid gets smaller and smaller, and right here, the last little bit of liquid disappears, and now we have pure vapor. Okay? That's called the lever rule, and you need to be able to use the lever rule to tell me how much of each phase we have. Okay? So the lever rule tells you how much of each phase. So if we look at this, we can see this is, let's see, it's about 3 over. So this would be about 0.76 if we just count the number of squares and see what fraction of the way this over. So that tells us XB, if we heat this stuff up to here, then we can say XB in the vapor phase is equal to about 0.76, right? So just by counting up the squares. Okay, now on the other hand, if we were to look at the liquid phase, So we come over here, go down here. That looks like it's about, so it looks like the mole fraction of B in the liquid phase is about 0.32. So basically, if we want to know the compositions, we don't use the lever rule. We just use where are the ends of the tie lines. So the lines that go across a two-phase region are called tie lines. So this whole region is a region where liquid plus vapor are coexisting. And so what this means is if you try to go anywhere in this region, this two-phase, that's supposed to be vapor plus liquid. If you're anywhere inside this two-phase region, as soon as you try to prepare a system that has that temperature and overall composition, it splits into two different phases. And we have a horizontal tie line saying you've got that liquid in equilibrium with that vapor. And so the ends of the tie lines give you the composition. One final point about the liquid vapor phase diagram, we can apply Gibbs phase rule to it. If I am here, we say, okay, Gibbs phase rule is degrees of freedom is equal to components minus the number of phases plus 2. All right, well, I've got two components. I've got A and B. If I'm in this two-phase region, I've got two phases. Okay, so that comes out to 2. But we have to remember, in this phase diagram, we took away one of our variables. We said that this was P constant, right? On these diagrams, and typically the P, if it's, most commonly the P would be at 1 bar, and we're just looking at the effective temperature. So because we took away a variable, we have to account for that. And so what we can say is, because P is fixed, we can say that we have the degree of freedom prime. Basically, the degrees of freedom on that diagram is we're losing a variable. And so it's equal to 1. What does that mean? That means that if I try to go in here, I split up into two phases, one there and one there, and those two phases each have 1 degree of freedom. If I lower the temperature to here, the composition of those two phases changes to follow suit, right? So if I give you this temperature, you can give me, just by looking at the diagram, what the composition is. We can't choose it, so we only get to choose one variable. If we choose temperature, we get composition. If you give me a composition of the vapor phase, I know what temperature we're at. Okay, so there's 1 degree of freedom on the diagram because we've lost a degree of freedom here. Okay, I guess there is actually one more topic after this, which is non-ideal mixtures. We just did ideal mixtures, and so let's look at a case where we have positive deviation from Raoult's law. Well, in this case, what's going to happen if we have a slight positive deviation? Remember, that means the vapor pressure is higher, which is going to make the boiling point lower. Is that that sort of two-phase region sags a bit, right? So we've got a little bit, because positive deviations, higher vapor pressure means lower boiling temperature, right? So this just gets pushed down a bit from what we showed you earlier. However, let's imagine that, let's call this a small positive deviation. What if we have a large positive deviation from Raoult's law? Well, if we have a large one, if we just keep pushing down, what happens is the mixture, remember, large positive deviation means that the components do not have a favorable interaction. They don't interact favorably, so they try to get out of the liquid phase. That's going to make their boiling point lower quite a bit, and eventually this whole thing just sags even lower. And so we get something that looks like this. So we've still got liquid, we've still got vapor, we still have these vapor-liquid coexistence regions. But here we have a point where they touch, everything touches at a point. And that composition is an azeotrope. And that just means that it boils without changing. Okay? Boils without changing is what that means. Because if you take a mixture that's azeotropic at that composition and you boil it, it has a nice sharp boiling point, and the vapor and liquid have exactly the same composition. It's just like boiling a pure liquid. In fact, if I gave you a vial and told you it was a pure liquid and it really was an azeotrope, you wouldn't be able to tell the difference. You get a nice sharp boiling point, and if you took the vapor and condensed it, it would have the same composition. So azeotropes are kind of interesting that way. And this is called a low boiling azeotrope. And you can imagine what would happen if you had a large negative deviation from Raoult's law. It would be just the opposite. And I'll just sketch one out really quickly. If you had a large negative deviation from Raoult's law, that means that the vapor pressure is low because the components have a very favorable interaction with one another. So they tend to stay in the liquid phase. They have a low vapor pressure, which corresponds to a high boiling temperature, and you get a phase diagram that looks like that. So you've got liquid, vapor, and then two liquid plus vapor coexistence regions. And here, you can see what happens if I come with the azeotropic composition. It boils without changing there. So that's what happens if you have extreme deviation from Raoult's law.